Hello, everyone, and welcome. Today, we're diving into the world of probability and exploring several powerful techniques to help us solve complex problems. We'll be looking at a few key tools. By the end of this lecture, you will be able to use Venn diagrams, tree diagrams, and tables to calculate probabilities. We'll also cover the essential formulas for combined events, conditional probability, and independent events. Let's get started with a very visual tool. First up, Venn diagrams. You've likely seen these before. They are incredibly useful for representing information about sets and showing where they overlap. We can use them to visualize a situation, which makes calculating probabilities much more intuitive. A key tip when filling in a Venn diagram is to always start from the inside, the intersection, and work your way outwards. Let's walk through an example. In a school year of 60 students, 32 study geography and 40 study biology. We know that 18 students study both subjects. Our goal is to find the probability that a randomly selected student studies neither geography nor biology. First, let's draw our Venn diagram. We'll have two overlapping circles, one for biology, which we'll label B, and one for geography, labeled G. The entire diagram is enclosed in a rectangle, which represents our total sample space of 60 students. As I mentioned, we start in the middle. The intersection represents the students who study both subjects. The problem tells us that 18 students study both, so we'll put the number 18 right in that overlapping section. Now let's work outwards. We know that 40 students in total study biology. This means the entire B circle must contain 40 students. Since 18 of them are already accounted for in the intersection, we can find the number who only study biology. We take the total for biology 40 and subtract the 18 who also study geography. This leaves us with 22 students who only study biology. We'll write 22 in the part of the B circle that doesn't overlap. We do the same for geography. The total number of geography students is 32. Again, 18 of these are in the intersection. So, to find those who only study geography, we calculate 32 minus 18, which gives us 14. We'll place 14 in the non-overlapping part of the G circle. So now our diagram shows 22 students in biology only, 14 in geography only, and 18 in both. But we're not done. The problem asks for the students who study neither subject. These students will be inside the rectangle but outside of both circles. We know there are 60 students in total. Let's add up the students we've placed so far. 22 plus 18 plus 14 equals 54. So 54 students study at least one of the subjects. To find the number studying neither, we subtract this from the total number of students. 60 minus 54 gives us 6. So 6 students study neither subject. We write this number inside the box, but outside the circles. Finally, we can answer the question, what is the probability that a randomly selected student studies neither subject? The probability is the number of favorable outcomes divided by the total number of outcomes. Here it's 6 students out of a total of 60. So the probability is 6 over 60, which simplifies to 1 over 10, or 0.1. So, by systematically filling in the Venn diagram from the inside out, we can easily organize the information and solve the probability problem. We've now seen how to use a Venn diagram to find probabilities for overlapping sets. Next, let's look at another powerful tool, tree diagrams. These are especially useful when we're dealing with a sequence of events, particularly when the outcome of one event affects the outcome of the next. The key with tree diagrams is to multiply probabilities along the branches to find the probability of a specific sequence of outcomes, and then add the probabilities of the final outcomes that fit our criteria. Let's consider this example. In a city, the probability of it raining is 1/4. If it rains, the probability of Anya traveling by car is 2/3. If it does not rain, the probability she travels by car is 1/2. We want to find the overall probability that Anya travels by car. We'll start by drawing the first set of branches for our first event, whether it rains or not. Let's use R for rain and R prime for not rain. From our starting point, we draw 2 branches. The top branch is for rain, with a probability of 1/4. The bottom branch is for not raining. Since these are the only 2 possibilities, the probability of it not raining must be 1 minus 1/4, which is 3/4. Now, from the end of each of these branches, we draw the next set of branches for our second event, whether Anya travels by car or not. Let's use C for car and C prime for not car. First, let's look at the rain branch. The problem states that if it rains, the probability of her taking the car is 2/3. So from the R node, we draw a branch for C with probability 2/3. The other possibility is not taking the car, so that branch will have a probability of 1 minus 2/3, which is 1/3. Now let's do the same for the not rain branch. If it doesn't rain, the probability of her taking the car is 1/2. So from the R prime node, we draw a branch for C with probability 1/2. This means the probability of not taking the car is also 1/2. Our tree diagram is complete. Now, to find the probability of any full path, we multiply the probabilities along its branches. For the top path, rain and car, the probability is 1/4 times 2/3, which is 1/6. For rain and not car, it's 1/4 times 1/3, or 1/12. For not rain and car, it's 3/4 times 1/2, or 3/8. And for not rain and not car, it's also 3/4 times 1/2, which is 3/8. The question asks for the overall probability that Anya travels by car. This can happen in two ways. It rains and she takes the car, or it does not rain and she takes the car. Notice the two outcomes that end in C. We need to add the probabilities of these two distinct outcomes. So we add the probability of the first case, 1/6, to the probability of the second case, 3/8. To add these fractions, we find a common denominator, which is 24. 1/6 becomes 4/24, and 3/8 becomes 9/24. Adding them together, we get 13/24. So the overall probability of Anya traveling by car is 13/24. This example clearly shows the two main rules for tree diagrams. Multiply along the branches for a sequence of events, and add the results for the different outcomes that satisfy the condition. This is a fundamental technique for handling sequential probability. Sometimes, the most straightforward way to find probabilities is to simply list all possible outcomes. This is where sample space diagrams come in handy. They are particularly useful for experiments with a limited number of equally likely outcomes, like rolling dice. Let's take this example. 2 fair standard four-sided dice are rolled. We want to find the probability that the sum of the numbers is larger than 6. We can create a simple table or a sample space diagram to show all possible sums. The columns will represent the outcome of the first die, which can be 1, 2, 3, or 4. The rows will represent the outcome of the second die, also 1, 2, 3, or 4. Now we fill in each cell of the grid with the sum of the row and column values. In the first row, we have 1 plus 1 equal 2, 1 plus 2 equal 3, 1 plus 3 4, 1 plus 4 5. In the second row, 2 plus 1 3, 2 plus 2 4, and so on. We complete the entire grid. This grid now shows every single possible outcome. How many outcomes are there in total? Since it's a 4x4 grid, there are 16 possible outcomes in our sample space. Each of these is equally likely. The question asks for the probability that the sum is larger than 6. This means we are looking for sums of 7 or 8. Let's look at our table and identify the outcomes that are greater than 6. We have a 7 here, another 7 here, and an 8 here. That's a total of 3 outcomes. So we have 3 favorable outcomes out of a total of 16 possible outcomes. The probability is therefore 3 divided by 16. And that's our final answer. Sample space diagrams provide a clear and exhaustive way to see all possibilities, making it simple to count outcomes and calculate probabilities. We have now covered how to use a sample space diagram to list all outcomes and find a probability. This method is very effective when the number of outcomes is manageable. Similar to sample space diagrams, we can use tables of outcomes to organize data from a survey or experiment. When information is given in a table, it's often a good idea to start by finding the totals for each row and column. Let's look at this example. We have a table showing the interaction between the type of book, fiction or nonfiction, and its size, number of pages, in a random sample of library books. The first step, which is almost always helpful, is to add a total row and a total column to our table. Let's calculate these totals. For the rows, 23 plus 3 is 26, 28 plus 6 is 34, 8 plus 12 is 20. Now for the columns, 23 plus 28 plus 8 is 59, 3 plus 6 plus 12 is 21. And finally, the grand total. We can either add the row totals, 26 plus 34 plus 20, or the column totals 59 plus 21. Both give us 80. This is the total number of books in our sample. Now that our table is complete, we can answer the questions. Part A asks for the probability that a randomly selected book is fiction. We look at our total row. The total number of fiction books is 59. The grand total of all books is 80. So the probability of selecting a fiction book is simply 59 out of 80. This is a straightforward probability calculation. Part B is a bit different. It says, Alessia randomly selects a non-fiction book. Find the probability that it has 0 to 200 pages. This is an example of conditional probability, which we'll define more formally soon. The key phrase here is selects a non-fiction book. This means we are no longer considering all 80 books. Our sample space has been restricted. We are only looking at the non-fiction books. From our table, we see there are a total of 21 non-fiction books. This is our new denominator. Now, within this group of 21 non-fiction books, how many have 0 to 200 pages? Looking at the table, we find the cell where the 0 to 200 pages row and the non-fiction column intersect. The value is 3. So the probability is 3 out of 21, which simplifies to 1/7. By using the table and understanding how the condition restricts our sample space, we can solve these types of problems effectively. We've now seen how to use tables of outcomes for both simple and conditional probability and the importance of calculating totals first. Let's talk about combined events. This is when we want to find the probability of either event A or event B occurring. In set notation, this is the union of A and B. If we think about our Venn diagram, the probability of A or B is the probability of being anywhere in the shaded region, which covers all of A and all of B. A common mistake is to simply add the probability of A and the probability of B. Why is this wrong? Because if we do that, we count the intersection, the part where both A and B happen, twice. Imagine coloring in all of A and then coloring in all of B. The overlapping part gets colored 2 times. To correct for this double counting, we need to subtract the probability of the intersection 1 time. This gives us the general addition rule for probability. The probability of A or B is the probability of A plus the probability of B minus the probability of A and B. Let's use this formula in an example. Suppose we know the probability of A is 0.4, the probability of B is 0.3, and the probability of A or B is 0.5. We need to find the probability of A and B, which is the intersection. We'll start with our addition rule formula. P of A union B equals P of A plus P of B minus P of A intersect B. Now, we substitute the values we were given into the equation. 0.5 goes in for PA union B, 0.4 for PA, and 0.3 for PB. Let's simplify the right side. 0.4 plus 0.3 is 0.7, so 0.5 equals 0.7 minus the probability of the intersection. Now we just need to rearrange the equation to solve for PA intersect B. We can add PA intersect B to both sides and subtract 0.5 from both sides. This gives us P of A intersect B equals 0.7 minus 0.5, which is 0.2. So the probability of both events A and B occurring is 0.2. This demonstrates how the addition rule connects the probabilities of individual events, their union, and their intersection, allowing us to find any one of these if we know the others. Now let's consider a special case of combined events called mutually exclusive events. 2 events are mutually exclusive if they cannot both happen at the same time. For example, when you roll a single die, the event rolling a 1 and the event rolling a 6 are mutually exclusive. You can't do both in one roll. In a Venn diagram, mutually exclusive events have no overlap. The circles for events A and B do not touch. This means their intersection is empty. Mathematically, this means the probability of both A and B happening, PA intersect B, is 0. There is no chance of both occurring simultaneously. How does this affect our addition rule? Let's look at the general formula again. The rule is PA or B equals PA plus PB minus PA and B. If the events are mutually exclusive, the last term, P of A intersect B, is 0. So the formula simplifies. For mutually exclusive events, the probability of A or B happening is simply the probability of A plus the probability of B. We don't need to subtract anything because there's no overlap to double count. Let's apply this to an example. If 2 events A and B are mutually exclusive, and we know PA is 0.5 and PA or B is 0.8, what is PB? Since the events are mutually exclusive, we can use our simplified formula. P of A union B equals P of A plus P of B. Now we plug in the values we know. Point equals 0.5 plus P of B. To find PB, we just subtract 0.5 from both sides. This gives us PB equals 0.3. It's a very straightforward calculation once we recognize the events are mutually exclusive. So, remember, if events can't happen together, their intersection is 0, and you can just add their probabilities to find the probability of one or the other occurring. We've touched on this idea already, but let's formally define it. Conditional probability is the probability of an event happening, given that another event has already occurred. We write this as PA vertical bar B, and we read it as the probability of A given B. The key idea is that the occurrence of event B might change the probability of event A. Let's look at a classic example. A standard deck of 52 cards has 13 hearts. If we draw a card, don't replace it, and see that it's a heart, what is the probability that the second card we draw is also a heart? The condition here is that the first card was a heart. This changes our sample space. Originally, we had 52 cards, but since we drew one card and didn't put it back, there are now only 51 cards left. Also, since that first card was a heart, there are now only 12 hearts remaining in the deck. So the probability of the second card being a heart, given the first was a heart, is based on this new situation. The probability is the number of remaining hearts, which is 12, divided by the total number of remaining cards, which is 51. We can simplify this fraction by dividing the top and bottom by 3, which gives us 4 over 17. This intuitive approach leads us to a general formula. Let's think about it with a Venn diagram. When we say given B, we are essentially ignoring everything outside of event B. Our new universe or sample space is just B. The probability of B, PB, becomes our new denominator. Within this new universe of B, what's the probability that A also happens? Well, the part of A that can happen is the part that is also inside B, which is the intersection, A intersect B. So our favorable outcome is the intersection. This gives us the formal formula for conditional probability. The probability of A given B is the probability of A and B divided by the probability of B. This formula is one of the most important in probability theory. Let's use this formula on another example. The probability a student studies only French is 0.4. The probability they study both French and Spanish is 0.1. Find the probability a student studies Spanish given they study French. First, let's find the total probability of studying French. This includes those who study only French and those who study both. So P of French is 0.4 plus 0.1, which equals 0.5. This will be our denominator, our PB. The intersection, P, Spanish, and French, is given as 0.1. This is our numerator. Using the formula, P, Spanish given French is 0.1 divided by 0.5, which equals 0.2. So there is a 0.2 probability that a student studies Spanish, given that we know they study French. Our final key concept is independent events. Two events are independent if the occurrence of one does not affect the probability of the other occurring. For example, if you flip a coin and roll a die, the outcome of the coin flip has no impact on the outcome of the die roll. They are independent. In terms of conditional probability, this means that the probability of A given B is just the probability of A. Knowing that B happened gives us no new information about A. Let's see what this means for our conditional probability formula. The formula is P of A given B equals PA and B divided by P of B. If the events are independent, we can replace PA given B with just PA. So for independent events, PA equals PA and B over PB. Now, if we rearrange this equation by multiplying both sides by PB, we get a very useful rule. The probability of two independent events both happening is simply the product of their individual probabilities. This is the multiplication rule for independent events. Let's look at an example. The probability of a randomly chosen person being male is 0.52. The probability of them being of Irish origin is 0.18. If these two characteristics are independent, what is the probability of selecting a male of Irish origin? The problem states the events are independent, so we can use our multiplication rule. The probability of being male and Irish is the probability of being male times the probability of being Irish. We just plug in the numbers. That's 0.52 multiplied by 0.18. Calculating this gives us 0.0936. So there's about a 9.4% chance of selecting a person who is both male and of Irish origin, assuming these traits are independent. It's important to note that assuming independence is often a modeling choice. In reality, there might be small links between events. For this example, genetic or social factors might mean that being male and being of Irish origin are not perfectly independent. But for many problems, assuming independence is a valid and useful simplification. All right, let's test our understanding with a problem that often trips students up. This will require us to choose the correct rule. A bag contains 10 balls, labeled 1 through 10. Hannah picks one at random. What is the probability she gets a prime number or an even number? First, let's identify our events and their probabilities. Event A is picking a prime number. Event B is picking an even number. The prime numbers between 1 and 10 are 2, 3, 5, and 7. There are 4 of them, so P up prime is 4/10. The even numbers are 2, 4, 6, 8, and 10. There are 5 of them, so P a even is 5/10. The question asks for P of prime or even. Let's look at a common incorrect solution. Solution 1 simply adds the two probabilities. 4/10 plus 5/10 equals 9/10. Take a moment to think. Why is this incorrect? This is wrong because the events are not mutually exclusive. Is there a number that is both prime and even? Yes, the number 2. Because there's an overlap, we have double counted it. Solution 1 adds the ball 2 once as a prime and a second time as an even number. To correct this, we must use the full addition rule. The correct approach is to use the formula PA or B equals PA plus PB minus PA and B. So we have 4/10 plus 5/10, and we subtract the intersection, which is 1/10. This gives us 8/10. This is the correct answer. Let's quickly check another common error. Solution 3 tries to find the intersection by multiplying the probabilities. This would only be correct if the events were independent. But are they? They are not. Knowing a number is prime makes it much less likely to be even. Only the number 2 works. Since one event affects the other's probability, they are not independent, and we cannot use the multiplication rule here. We have to find the intersection by direct counting. This example highlights the importance of first checking if events are mutually exclusive or independent before applying a simplified formula. All right, let's quickly recap what we've covered today. We've learned to use visual tools like Venn diagrams, tree diagrams, and tables to organize information and solve probability problems. We've also established the key formulas that govern probability: the addition rule for combined events, the formula for conditional probability, and the multiplication rule for independent events. We saw how these concepts are distinct. Mutually exclusive events have no overlap, while independent events have probabilities that don't affect each other. Understanding which case you're dealing with is the key to choosing the right formula. These techniques are the foundation for tackling a wide range of probability questions. The best way to master them is through practice. Thank you for your attention.